So, hello, grade 12 students. In this session, we're going to continue with our chapter, the nervous system, with chapter 9, the function of the neurons. Yesterday, we started with chapter 9, document 1, about the resting potential on page 182. So, we talk about the resting potential. We said that we have the causes of the resting potential. What are the causes? How do you know that we have an action potential and a resting potential, sorry. So we insert into a giant action of a squid, a microelectrode that contain the KCl solution, and then we observe the differences and the potential difference as we introduce the experiment by observing it on the oscilloscope, and then we observe the difference and the concentrations in the intracellular and the extracellular medium regarding the ions, the chloride ion, the potassium ion, the sodium ions, the intracellular and the extracellular medium in both marine animals and the mammal. And we identify the selective permeability of the membrane by observing the experiment in document E, allowing only K pluses who are highly permeable to K plus, and it allows the diffusion. So identify the definition of the diffusion. وحكينا about diffusion. We said that diffusion is the movement of a substance from a medium of high concentration toward a medium of low concentration with the concentration gradient. حكينا about two different types of transport. We have something called the passive transport and something called the active. Passive transport, it takes place with the concentration gradient. It doesn't need energy. So it moves toward the high concentration, toward the high number. While active, it takes the place against the concentration gradient, meaning that it needs energy. This energy should be supplied in the form of ATP, adenosine triphosphate. This is the source of energy that is used by the cell in our body. So here I said that ADP, it's going to be phosphorylated, meaning that addition of phosphate to ATP, to change into ATP, which is the source of energy. If you remember dinitrophenol, DMP, it inhibits this process. It inhibits the phosphorylation of the ADP into ATP. And we move here to document 2 about the action potential. Document 2 showing that the resting potential, it is the easily disrupted by stimulation. Whenever we have a resting potential, this resting potential can be easily disrupted whenever we have a stimulus. This disruption at the origin of the nerve impulse traverses the cell. So how is the action potential triggered? How do we have an action potential and what is due to? So recording of an action potential in paragraph 1. Remember, I'm going to talk in this paragraph about the phases of the action potential that we studied about them in the last week, about the phases of the action potential whenever we have the resting potential, depolarization, inversion of polarity, repolarization, hyperpolarization, and going back to the resting state. Remember about these phases of the action potential. So recording of the action potential. So when stimulated in neurons, they are subjected to modification of their membrane potential. So document A schematizes the experimental setup that allows us to study the response of the giant axon of a squid to stimulation. The graph obtained correspond to an action potential, which is in document B in this document. So here we have stimulating electrodes. One of them is run outside. One is B is placed to the reference electrode. A is the recording, and S is the stimulating electrode, and we observe the response on the oscilloscope. If you see in document B, we have the electrical interpretation of the phases of the action potential. So these electric interpretation we have, if you remember, when we talk about the graph of the action potential, the phases of the action potential here, we have number one. Number one is at minus 70. So it will correspond to the resting potential, which is the resting potential at rest. There is no stimulus. While 2, it corresponds to what? 2, it corresponds to the stimulation. We have here hypopolarization. Okay, this is called the artifact, if you remember. Okay, and then 43, we have the depolarization. Depolarization meaning that moving toward the positive and getting rid of the polarity, of the negativity. And here, this phase, if you remember, we name it part 4 here. This is the inversion of polarity. Number 4, we're moving back to the polarization, to the negativity. So this is called the repolarization. While number 5, it's corresponding to the polarity higher than the normal. So it's the hyperpolarization. And number 6, it corresponds to what? Number 6 is correspond to the returning back to the resting potential, which is the minus 70 millivolts. So these are the different phases of the action potential. Remember when we talked about them last time, we said that we have 7 phases. Since I put the number 4 for the inversion of polarity. So here we have phase 1, we have the resting potential where potential difference is equal to minus 70 millivolt. Number 2 is the hypopolarization, decrease in the negativity, but there is not an action potential. The action potential starts here at the depolarization whenever it reaches the threshold. And then we have inversion of polarity from the positive to the negative, going back to the negative, the repolarization. This phase 5, it's the hyperpolarization, and 6, it's returning back to the resting state. So these are the different phases of the action potential that already we talk about them. So, Ionic interpretation of the action potential. Proteins with pores or protein channels, they are located on the sides of the cell membrane. So here they are large molecules, they are located within the cell membrane. They help in the passage of the small ions. So they facilitate the passage of the ions, and they are called the ionic channels or the ion channels. These channels, they have an important role. They open upon stimulation, and they are called the voltage dependent channels or voltage gated channels. Their opening is controlled by the membrane potential. This is the figure showing the ion channels of the membrane. So we have K plus channels with passive function, and we have the Na plus channels. And also following an axial stimulation, we observe modification of the permeability of both Na plus and K plus channels. This modification will determine the phases of the action potential. Let's see here step by step. We have as the resting phase. At the resting phase, what's happening here? Pay attention here in the document D, variation of the flow of ions during an action potential. Here I'm talking in document D. So pay attention to the different phases. Document D, what do we have? We have both channels. We have the sodium channels and we have the potassium channels. Sodium channels, Na plus is going outside the cellular medium. It's going to the extracellular medium, while Na plus they are moving to the intracellular. While moving for depolarization. Depolarization meaning that getting rid of the negativity. So Na plus is entering inside the cell, which decreases the negativity, and also the K plus. Moving for the repolarization phase. Repolarization, it's going back again to the negativity. So this is the repolarization phase. In the repolarization, we're going back to the negative. So this is going back to the negative. So here it's the repolarization phase. So first phase is depolarization. This is the depolarization. Here we have the repolarization going back to the negative. So what's happening here? What's happening as the Na plus channels they open or they decrease, so they have an effect on the different phases. So these channels, Na plus K plus channels, they have important role in determining the phases of the action potential and as well as the recorded potential difference. Moving for the last one, the last phase is the hyperpolarization. Hyperpolarization, we have negativity more than the usual. So hyperpolarization decreases below minus 70, well, minus 75, minus 80 millivolt. So this is because of the flow of the A plus and the Na plus channels. In order to understand this and to explain this figure, document D, we have to move to part 3 in the following the documents. So here, action potential, what does correspond to? Already we solved this before, and different phases, already we talked about them and also we drew them before. So I want to move to part 3. Part 3, we have to relate the different phases of the action potential to the corresponding modification in the membrane permeability. So permeability of the membrane and we have to deduce the origin of the action potential. These nodes already we talk about them when we talk about the ionic interpretation, okay, of the action potential. So to study about this, during depolarization, the number depolarization, pay attention here. During the depolarization, a number of Na plus channels open increases from 0 sorry to 40. So here, as the number of the gate channels increase from 0 to about 40. What happened for the action potential? Here, I'm talking about this. During the depolarization, increases to about 40 millivolt. What happened for the action potential? Sure, the action potential, or it increases. So here, during depolarization, the number of Na plus increases from 0 to 40 per microsecond milliseconds. The number of gated Na plus channels is almost zero. It's about zero. It's almost null. Okay, so it's almost null. It's almost zero. How can we identify which one is the Na plus and which one is the K plus? Pay attention here to the figure. This one in purple. Okay, the violet one. This is the channel. Okay, while this one, and let's say make it in red, this is for the Na plus channels, and the green one is for the action potential. So pay attention to this. Okay, the first one, the violet one, which is similar to the color of the K plus, is representing the K plus channels. Also, the one in, let's say, Bordeaux, if you want, this one is for the Na plus channels, and the one in green is for the action potential. Okay, so let's start. Let's talk about the depolarization. I want to hear volunteer to talk about the depolarization phase. What happened for the K plus, for the Na plus, as well as for the action potential. Yes, let's start. I want to hear a volunteer. First of all, the violet one is for the K plus channel. So if you want to write over this, this one is for the K plus. Let's make it here. This one is for the K plus. This color is for the uh, Na plus channels, and the green one it's for the action potential. Yes. First, I need a volunteer to start with this. Let's start with something new. I need to hear Summer. Good morning, yeah, Summer. Summer, good morning. Hello.
Good morning.
Okay, Summer. Let's start first with the depolarization phase. Depolarization, I'm going to talk about this phase. So what do you think about the gate, the Na plus channels? What happened for them? Here you can move your work here. This is the about the number of the open channels per micro milliseconds of the membrane. Okay, so here first I want you to start with the Na plus channels. Na plus channel is the one in purple. Okay, يعني this one. This is for the Na plus. What happened for the number of Na plus channels? Increases or decreases?
It increases
Okay, increases from 0 to what? To about, if you want to move here, it increases to about what? To about
40.
40. So, and the number of K plus channels, this one, the number of K plus channels is was approximately none. Approximately it was 0. So what happened during the
Yeah.
depolarization? The action potential, it increases or it decreases? The one in green, this is the action potential.
It increases.
We have an increase in the action potential. Okay, so thank you, Summer. So during depolarization, the number of Na plus channels increases from 0 to 40, and the number of the K plus channels was approximately 0, almost null. The potential difference, which is the delta V, it increases across the membrane from 70, -70 to about plus 30 millivolt. So what does this mean? This means that depolarization is caused by what? By the opening of Na plus. So Na plus channels they open and they enter from the extracellular medium toward the intracellular medium, and they cause the depolarization phase. So this is the first phase during the depolarization. During depolarization, Na plus channels they open, K plus they are almost zero, open K plus channels, or the number of open K plus channels they are almost zero, almost null, and this leads to the entrance of the Na plus from the extracellular toward the intracellular medium, and this leads to the depolarization phase. Let's move now to talk about the other phase, which is the repolarization phase. What's happening in the repolarization phase? Repolarization, which is here. This is the repolarization phase. Okay? Okay, I want to volunteer to explain this graph during the repolarization, which is here and this phase. يلا, let's move forward. Let's have Muhammad. يلا Muhammad, say it. During repolarization phase, what happened?
Yes, okay. So you want to talk about repolarization?
Repolarization, yes, the one in the circle here. During this phase, they will in the white color.
Okay.
Okay?
So during the time of repolarization,
Okay.
from one.
No need to talk about the time. During repolarization phase, if you want. Muhammad Zayed, you're here. Hello. Okay, let's move to other. Maybe Muhammad has a problem in the connection. Let's move to Ali. Ali Hariri. Good morning.
Good morning.
Okay, Ali. Yalla. Let's move instead of Muhammad. Whenever Muhammad say you can take another.
Yes, I'm here. I'm here.
I'm here.
Yes, the
Okay,
internet
yeah.
isn't good.
Okay, yeah, no
So
problem.
during
Ali, next question is yours. Yeah. Yes, Muhammad.
Okay.
Continue.
during the state of repolarization, the
Yes.
Na channels decreases from 40 to 0,
So
and
about
the action
zero.
potential also increases from 30 to about 20, 60 or 70. So this indicates the going back to initial state.
Going back to the repolarization, going back to the initial state. That's it. Okay, great. So here we'll have to talk about the repolarization. So number of K plus channels, you didn't mention this, Muhammad, but the number of K plus, it decreases. And the number of Na plus channels here. So the number of Na plus channels here decreases. Here, the number of Na plus channels decreases. The number of open K plus increases from 0 to from 0 to from 40 to 0, and the number of K plus increases to about 20. So the potential difference decreases to about minus 70 millivolt. What does this indicate? This indicates that the repolarization is caused by the opening of K plus and the flow of K plus from the intra to the extracellular medium. Why the last one? Hyperpolarization. Yes, Ali, hyperpolarization. What happened during the hyperpolarization?
The number of K plus channels opened decreases from 20 to 0.
Yes, and that of
The
Na
number
plus
of Na plus channels remains constant at 0.
Remains null, and the action potential
Decreases below 60, then
below
becomes 0.
that's below the resting potential, below the one of the resting potential. Okay, so here during the hyperpolarization, Na plus channels remains zero. The number of up in K plus decreases slightly to become zero at the end, and the potential difference it decreases below the minus 70. So it decreases below the one of the resting potential. What does this indicate? This indicates that the hyperpolarization is caused by what? By the flow of small amount of K plus from enter to the extra. So therefore, as a conclusion here in part 3b, the action potential is caused by the change in the permeability of the membrane of the nerve fiber to both Na plus channels, Na plus ions, and K plus ion through their channels, Na plus K plus channels. So action potential is caused mainly by the change in the permeability of the membrane of the nerve fiber to both Na plus and K plus ions. So you have to pay attention to this. So during the depolarization, it's caused by opening of Na plus channels and entrance of these ions from the extra to the intra. So this leads to the depolarization. So more positivity accumulate. Repolarization caused by opening of K plus and their flow from the intra to the extra. So we go back to that repolarization going back to the negativity, whereas the hyperpolarization is caused by the flow of small amount of K plus from the intra to the extra, as well as the number of The Na plus channel is remains approximately zero, it stays zero. So action potential, keep it in your mind, is caused by the change in the permeability of what? Of the membrane to both Na plus ions and the K plus ions. And this is the origin of the action potential. Already we talked about this when we described the different phases of the action potential and the ionic interpretation, if you remember, whenever we started with the introduction of the neurophysiology. Okay, so document 3, starting with the nerve impulse and action potential, page 187. So nerve impulse and the action potentials. Action potentials, they are elementary signals that rise from the rapid triggering of neural impulses that propagate along the nerve fibers. What are the characteristics of the nerve impulse and how does it propagate? Here I'm going to talk about effective, ineffective. We're going to talk about effective simulation, ineffective simulation, about the threshold of excitation, the characteristic of the nervous message in the nerve fiber, and so on. If you remember, when we talk about the effective, ineffective threshold of excitation, threshold of depolarization, whenever we started. Characteristics of the nerve impulse in a nerve fiber. We have an isolated nerve fiber subjected to stimulation of increasing intensity in such a way that I1, I2, and I3 they are below the threshold, where I4, I5, and I6 they are above the threshold. These recordings obtained are presented in document A, showing the experimental setup, traces obtained in the figure part 2. So part 1, we have the experimental setup. We have stimulating electrode S1 and S2. Here they are found, stimulating electrodes S1 and S2. We have recording electrodes R1 and R2, and here they are connected to the oscilloscope. So here we have recording on electrodes in the oscilloscope 1 and recording in oscilloscope 2. So what's happening? What is the difference in the brain potential and so on? So let's start step by step. I want to here to interpret. Already we did this together. I wanted to interpret the experiments done and the oscilloscope 1. So I want here to Rama to start. Rama, we applied three different stimulations of increasing intensities. I1, I2, and I3, they are below the threshold, while I4, I5, and I6, they are above the threshold. First of all, before we start, I want to ask you, Rama, what do you remember about the threshold of excitation? What does this mean? What does the threshold of excitation represent? Before we start with the threshold of depolarization. Yes, Rama, can you hear me? Or maybe Rama has a problem in her mic. Okay, let's move to Dana. Dana, good morning. Maybe Rama has a problem in her microphone. So Dana, good morning. Good morning, Dana. Also, you had a problem in your microphone? I think the guy is only speaking. Unless I need a female. I need Selena now. Good morning, Selena.
Good morning.
So I want you to explain to me first, what do you remember about the threshold of excitation? What do you remember about this? Yes, Selena?
It's the minimum amount of action potential that must be reached.
This minimum intensity needed to trigger an action potential, right?
Yeah.
So if I want you, Selena, to start with interpretation for the first three intensities, I1, I2, and I3. They are below the threshold of depolarization. So how can you interpret this? After applying, remember when we did this before?
Yes.
Okay, yeah, do it.
After applying stimulations I1 and I2 and I3 less than the threshold of excitation,
Yes? There is action potential or there is no action potential?
There's no action potential.
What does this
This,
indicate?
this indicates that it is an ineffective stimulation.
They are ineffective stimulations. Very good. Thank you, Selena. So they are ineffective stimulations. Whereas after applying I4, what do you think that the idea? After applying I4, what do we have? Stimulation of intensity
After
I4.
applying intensities to I4,
And stimulation of intensity I4.
The potential increased to plus 30.
So we have an action potential
There was
is
action
recorded.
potential.
So what does this
Yes.
indicate? Pay attention to this. What does this indicate? That
This
I4 is what?
is the action potential.
As first, we have an action potential. So what does this indicate? Indicate that intensity of a stimulation I4 is an effective or ineffective stimulation.
It's an effective stimulation.
What do we call it? Has a special name. What do we call it? Do you remember? The first one to go is an action potential. What do we call it? Yes. Who can tell me? Let's move to Hadil. What do we call the first intensity that causes the appearance of the action potential? Do you remember? What do we call it, Hadil? It's the first one to cause the appearance of the action potential. What do we call it? Yes, Hadil. Good morning. It was the first one to cause an action potential. What do we call it? The females today, they are in silent mode. They are in vacation mode. What do you think, Ali? What do we call it? The first intensity that causes the appearance of the action potential.
Threshold of excitation.
Threshold of excitation. Thank you. Moving to, I need new students here. And the girls, they are in the silent mode. Summer, your mic is working. I think Summer is not working. So I want to talk here about this. Intensities after applying simulations of intensities I1, I2, and I3, there is no action potential recorded. They are below the threshold of depolarization. So they are said to be the ineffective stimulations. While after applying the stimulation of I4, this I4, it causes the appearance for the action potential for the first time. So it's said to be, as Ali said, is said to be the threshold of excitation, while I5 and I6, they causes the appearance of the action potential, but it's said to be effective stimulations, similar to O2 and the similar properties in this. Already, these we covered them before whenever we start with the introduction for the nervous system. In the second experiment, what did they do? In the second experiment, the nerve fiber is subjected to only one stimulation of intensity above the threshold. The response is recorded by 3 different oscilloscopes with recording electrodes placed at different distances from the stimulating electrodes. As you see here, all of them, the first one, O1, is the first one, so it reaches first. Then the second, it reaches second, O2, since it's placed at a farther. So they stimulate here, and here's the oscilloscope 1, oscilloscope 2, and oscilloscope 3. And here we have S1, S2. Whenever you see S from now on, the stimulating electrode, R, it's the recording electrodes, R1, R2, and R3. So here we have the nerve fiber, and they record them. O1 is recorded. First, the first one, the action potential is recorded earlier. O2, it's far from the stimulation, and R3, O3 is also far from the stimulation. So here, as they are near, the action potential will be recorded earlier. So these are the characteristics that show that all of them, they have the same amplitude. If you remember when we talk about this, so all of them, they have the same amplitude. So here, what I want from you to know that whenever we have an effective stimulation, so there is an action potential, there is no effective stimulation, meaning that it's below the threshold of depolarization, so there is no action potential, it's called ineffective. Above the threshold of depolarization, so we have an action potential, so it's an effective stimulation. The first one to cause an action potential is said to be the threshold of excitation. So these are the notes for today's session. We talk about document 2. So as I said, in document 2, you have to know that differences in each of the phases of hyperpolarization, depolarization, and repolarization phases. You have to read the graph. Here the graph is somehow complicated since they didn't give the legend, but they depend on the colors of the channels of the K plus, the Na plus, and also they give the green color for the action potential. So here you have to focus on this, what's happening in each of these phases, and already we covered most of them during the sessions last week. Okay.